What I want to do what my teacher, Krein, but not Mark Krein, his younger brother, Salim Krein, taught me to do. He always said that every lecture should start with repeating everything you have done before that in the course. And actually, he succeeded in this. So I will try to repeat a little bit. And by the way, when I was starting, I didn't explain those pictures. You will see all of them, but I'll tell you this example of periodic structure of photonic crystal. This is what's called Fermi surface. This is Bloch varieties that we'll be discussing again, or dispersion relation, and this Dirac cone. We'll touch upon those later. So what I wanted to remind you a little bit, so what we did, we introduced this Flaquet transform, which Flaquet knew nothing about. So it's a safe way to call it. And it's kind of Fourier transform. Actually, it is Fourier transform on the group of periods, which is the lattice, and nothing else. And after that, if you have a periodic operator, for instance, our standard example is Schrödinger with periodic and sufficiently nice potential, this operator expands into direct integral over the dual torus of operators depending on quasi-momentum or crystal momentum vector, where the advantage of this expansion is that each of those operators is an elliptic operator on a compact manifold on a torus, with all those caveats that it doesn't act on scalar functions but on sections of linear bundle. But in any case, these are very nice operators with discrete spectrum, and they depend analytically, and we saw even polynomially on K. By the way, I commit a crime here, which I will be committing all the time, since K is not a variable on the torus. Since K is in Rn, in dural Rn, and the torus is a quotient Rn over the dual lattice. But it will be convenient to write this way, remembering that actually it is essentially a local coordinate on the torus. Okay, now I wanted to say some absolutely trivial things, but I think they provide very useful intuition. So what does it tell us, this expansion? That the operator acts as follows. You do some kind of Fourier transform, Flaquet transform. Then after you take function f of x. After the Flaquet transform, you get function uf, which is now function of k, but with values that are functions of x. So this is still function of k. And what happens then, you multiply this vector function by this operator function of k, and then you invert Flaquet transform. It resembles very much the standard convolution operators. Like if you take the operators that acts as follows, it takes Fourier transform of your function, and then it multiplies by some symbol, and then it inverts Fourier transform. That's known to be a convolution, one of the simplest examples of pseudo-differential operators. And this is actually a very useful analogy, not only as an analogy, actually people have made rigorous use of this approach. So it's useful to think of this as a convolution, but when you have operator valued symbol here. Then what we did, we considered the dispersion relation, which is let me remind you, I want to make sure that I go in the right sequence since my memory is non-existent. So what we did, we took the spectrum of each h of k. So we have this picture where k, you should imagine multidimensional, n-dimensional, this spectral parameter lambda. For each k, we took the eigenvalues lambda j of k in increasing, non-decreasing order of the operator h of k. And then when k changes, and you only need to change it for, in the case when that we will be always assuming that our lattice is Zn, and then the dual lattice is 2 pi Zn, then you only need the values of k which belong to the cube 0 to 2 pi to the power n. If you go further, it's periodic with respect to k. So when you move k, those guys are changing, and they can do various things. They can collide, they can have complicated singularities since it's multidimensional case. But in any case, you have some graph of multiple valued function. So it's from k to collection of all lambda j's of k. And if you order them in non-decreasing order, then there is no natural labeling. Here it's lambda 1 of k, this is lambda 2 of k. Here this is lambda 3, and this is lambda 4, since we label them in increasing order. They are called band functions. Then another hint how you can imagine this operator. You think that you are dealing with operator like convolution here, only the symbol is multiple valued function rather than single valued. In some sense, it's correct, and it's very kind of useful thing to.
That ignores the k dependence of the eigenvectors.
What?
That ignores the k
Yes.
dependence of the eigenvectors.
Yeah, which I will address later. You need to expand into eigenvectors. You need to know that there are good eigenvectors for that. So this is then what we also know, exactly like in the case of multiplication. So it's essentially, after Fourier transform, it's more or less multiplication, operator of multiplication by multiple valued function. Again, Barry is right, ignoring presence of eigenfunctions, which I will mention later. Then we know that exactly like in the case of multiplication by a scalar function or convolution here, it's easy to prove that the spectrum of this whole direct integral is just the range of this multiple valued function. So we project all band functions on the spectral axis, and then you have natural labeling of those closed intervals. The first band function produces the first band, etc. Here we have two touching bands, which you have seen already many times. But unlike 1D, what can also happen, as we have discussed before, you can have overlapping bands. So if you have something like this, then the band coming from this band function will overlap with this band coming from that one. You remember that in 1D, it's prohibited by a very simple monotonicity argument. Just counting how many solutions, that equation of second order can have only two independent solutions. It prohibited those things. But it's not prohibited here. Then I made this remark, which is, so the formula that we had is a sigma of h is just the union over the whole torus of the spectra of those operators. And this very general result, if you have a direct integral with appropriate properties of those operators h of k, then this is true. But trivial but very useful remark is that you don't need to have all quasi-momenta. Actually, you can have only a dense subset S of quasi-momenta. And then you can take the union only over this subset. Certainly, after that, you need to take the closure. So there are at least two useful applications of this. One is that sometimes some values of quasi-momentum are not very nice. It doesn't happen to Schrödinger, but it does happen for Maxwell. If you consider Maxwell operator in periodic medium, I hope I will have time to address it a little bit later, then k equals 0 is really bad value of quasi-momentum. Some analyticity breaks down. Here everything is analytic with respect to k. Over there is some problem with analyticity, and in many questions sometimes you cannot ignore it, but sometimes, like finding the spectrum, you can safely just ignore k equals 0 and then take the closure. Another application is the Born-Karman approach to the spectrum, which is also a nice numerical thing. So how you can approach finding the spectrum of this operator? So then Born-Karman idea is, if this is the X space, the real space, is that you take, instead of, let's say this is your fundamental cube, fundamental domain, what you do, you start stretching this cube n to n times in each direction. Then you consider your operator in this cube, and find this, impose periodic conditions, just periodic, so that you deal with only periodic functions in this cube, and find the spectrum of this periodic problem. It's discrete spectrum. Then the claim is that if you take, in the limit, if you take the union of those spectra when you extend and then take the closure, you get the spectrum of your operator. And this is immediate consequence of this thing, since what happens is that the functions which have periods like 2 pi over n, they are all n periodic. They are all, should I think 2 pi is equal to, no, there is no 2 pi here. 2 pi is in the dual space. So essentially what is this, that if you take those exponents, then this exponent will be periodic when k dot x is in what I'm saying, when each component of k you remember on the unit cube, to get periodicity, each component should be multiple of 2 pi. Here it's sufficient that each component kj is multiple of 2 pi over n.
It's multiple. There's an integer.
Yeah. What it means that when you consider the spectrum of this big cube, you have, if n is large, you have a pretty dense net of quasi-momenta in the dual torus. And when n increases, So essentially what you do when you consider this periodic problem, you consider some epsilon net, where epsilon is 2 pi over n, on the 0 to pi lengths of k. And when you increase n, obviously those things get dense, and therefore easy conclusion is that if you take the limit of the spectrum when n goes to infinity, you will have the spectrum of your operator. And this is actually used pretty frequently in numerics. But it's the instance of the same conclusion, that if you can restrict yourself to a dense subset of values of quasi-momentum. By the way, an interesting note here, that you don't have to put periodic conditions. You can put essentially more or less anything. You can put Dirichlet conditions, and in the spectra will converge. However, it will be not nearly as good as periodic conditions. What happens is that when you what you do in Born-Karman approach, you just sample your dispersion relation on some subset, which means that you never get any values that didn't belong to dispersion curve before. You cannot get a value here. If you have a gap, that's me. So what you do, you sample your spectrum, your lambdas, on a subset of quasi-momenta. So what you get these values. Now, if you, it's just by construction. If you use Dirichlet conditions, you can get spectra here, where you should have a gap. What happens if you increase the size of the cube? This spurious spectrum will get thinner and thinner. In what sense? In the sense of density of states, which we'll discuss later. So it's kind of approximation anyway.
If you take the Dirichlet and you reflect properly, you get a periodic in a bigger one. What's the connection with that?
You still can get this Dirichlet spurious spectrum here.
Yeah, it has to appear.
And this is an issue, since when you compute, you don't know is this true gap or not. So if you compute with periodic conditions, you essentially very soon see that there is a gap. Otherwise, you need to compute density of states, and it will be low here, but it doesn't mean that there is no spectrum. It may be very thin spectrum. And actually, this was an issue, oh gosh, it was already 20 years ago, when people were working on creation of photonic crystals, which are described by periodic Maxwell operator, and the issue was opening of a spectral gap. And for a while, there were only failures. There was even article in Nature in the beginning of the 90s that said photonic crystals bite the dust. Since theoretical calculations predicted spectral gaps, experiments showed that there were none there. And finally, people found geometries where there is a gap. But how it was found, the evidence was numerical and experimental. But none of them can distinguish between very thin density of states and true gap. So you needed analytic confirmation. It was found. Figotin and myself then proved that this happens, but that's a little warning about different ways of compute. By the way, here in the UK there is a group which fights this spurious spectrum. Michael Levitin. Okay, so that's thing I wanted to say, and let me remind you the notions. The graph, the function itself multi-valued function is called dispersion relation. This is a relation between spectral parameter and as a function of quasi-momentum, and the graph of this dispersion relation is said to be Bloch variety of our operator. And I don't think there is standard notation. I will denote it B sub h, Bloch variety of corresponding to the operator h. And what I will be doing now, I will be discussing various properties of this variety. And I already mentioned before that they might look sometimes esoteric, but all of them are important for spectral theory, as we will see a little bit later. So let me find.
Yesterday you defined Bloch variety when both lambda and k were allowed to be complex.
Yes, I forgot to mention this, that actually we can allow, people say real or complex Bloch variety. I don't want to make distinction. Let's agree right away that Bloch variety, in Bloch variety, both k and lambda could be complex. So the definition is the following. B sub h is a set of pairs k lambda in Cn plus 1 such that the equation hk of u equals lambda u has non-zero solution. In other words, this non-zero solution has a Bloch-Flaquet form. This u will look as follows: e to the power I k x times the periodic function of x. So you can rephrase this as follows, that this is a set of k and lambdas such that there is an eigenfunction of your generalized eigenfunction of your operator which looks like this exponential times the periodic function. It's equivalent. And there is nothing prohibiting us from considering k and lambda complex. There is no certainly the operator will not be self-adjoint if k is complex, but otherwise it's kosher. Okay, so let me find the page where I stopped. We have the picture of this, and this is, I think, where we stopped last time. And I have just repeated all this. And now we will spend some time discussing various properties of this Bloch variety. First of all, analyticity. And the theorem is that if you consider this complicated and definitely singular surface in Cn plus 1, the claim is that it's an analytic set. Actually, it's a little bit better. I don't want to introduce other notions. In other words, what I mean by analytic set here is that this is a set of zeros, of all zeros of an analytic function. There is an analytic function of k and lambda such that the set of its zeros is exactly the set of points of Bloch variety. Not more and not less. Not only Bloch variety belongs to it, but it's exactly the set of all zeros of this function. And it's an important information about this variety. And I don't know with history, I don't know history nearly as well as Barry does, but I think that probably many people have noticed this, and I bet that physicists probably realize this, but the first publication I've seen is a paper by Wilcox where he proved this. But probably, as always, he is not the first. And let me give you an idea how you prove this. The idea is the following. What you do, There is old and well-established science about such things, which is not well known, unfortunately. Its one-dimensional version is known due to Kato's book. But here we are dealing with multi-dimensional situation, and so multi-dimensional several complex variables are important. And so what we do, let's consider the operator A of k, which is h of k minus lambda. And then our block variety is just the set of points where the kernel of the operator is not zero. There is non-zero kernel. Remember, h of k u equals lambda u for non-zero function u. Now what do we have here? We have a family of operators on the torus. Therefore, they are Fredholm operator and Fredholm operators in appropriate spaces. In the case of Schrödinger, if you consider this an operator from H2 on the torus to L2 on the torus, it will be what's called Fredholm operator. I remind you, this means that the range is closed, the kernel is finite dimensional, and co-kernel is also finite dimensional. And now if we look at the set of points, kernel of it's A of k lambda, sorry. And this is analytic family with respect to the parameters. Actually, it's polynomial family. If you recall the formula, one of the formulas for h of k, we will return to it later. It's a polynomial, in particular, analytic family of Fredholm operators. And you're looking at the set of points where there is kernel. The claim is that this set of points is always analytic. There is an analytic function which provides exactly the set of those points. The main statement is local, near the point. And then there is technique from several complex variables to conclude that there is global analytic functions. In several complex variables, you don't have a partition of unity, so it is not.
You could actually write down an explicit
Yes.
determinant.
Yes, I will talk about this, but it's not in general, in this general setup, when you might not have determinant, but you still have this statement. Whenever you have an analytic family of Fredholm operators, then the set of points where you have a kernel is always analytic. It could be the whole space. You can have kernel everywhere. Then it's a set of zeros of zero function. There is no contradiction. But otherwise, it's an analytic set. Now, first of all, locally, you can prove it as follows. If this were a matrix function, you would write the equation determinant of A is 0. That's all. Here is your analytic function. And there is an analog, as Barry mentioned, for Schrödinger operators. Here we'll talk about it later. But if this is an abstract Fredholm operator, this is still true. And here is the idea. I don't want to give you the whole proof, but Fredholm operator, even when it depends not necessarily analytically, but even continuously on parameters, you can always, near some value of parameter, you can always split it into two parts. One will be infinite dimensional and invertible, and another will be finite dimensional. And for finite dimensional, you can take the determinant. That's it. And this split can be made analytically. By the way, there is a big science about this, and I shamelessly refer to our survey, Zeidenberg, Krein, Kuchment, and Pankov. It's available in English. It's in Russian mass surveys. In 1975. So it has all kinds of stuff you can do with Fredholm or semi-Fredholm operator functions, continuous, smooth, or especially analytic. So locally, it is just reduced to matrix thing. It's non-trivial matter in complex variables to deduce from local global results, since there is no partition of unity, but there is special technique, Kazan problems, etc., which I don't want to touch. It is true. There is global function. However, you can say more. If you look at the slide, not only there is an entire function, what I am saying is, what I explained here is that there is an entire function that gives you this set. But actually, this is entire function of finite order. So it's of exponential order. P, any P bigger than dimension works. And this is something that you cannot get by hand waving like I used here. You need to do something more serious. And this is where determinants, regularized determinants come in. That actually you can do the thing with the determinant you did with the matrix, but the determinants will have to be infinite. You will have to take care of their convergence, etc. So I will say few words here, but I wanted to say something else which I forgot right now. Okay, so we'll see. So here is a theorem that there is entire function of finite order which gives you those zeros. And actually, if you remember, we discussed that k is not the right variable on the torus. The things are periodic with respect to k. Actually, you can make sure that this function is also periodic with respect to k. Its zeros will be periodic due to this second statement, since the Bloch variety is periodic with respect to k. But you can make this function sacrificing a little bit the order of growth. And this happens to be important in various kinds, improving various kinds of theorems, where you do need to have estimates on this function, not just existence of an entire function. Now I recalled what I wanted to say about 1D case. In 1D case, this function looks as follows. Our discriminant minus 2 cosine k. If you remember, we have spectrum whenever discriminant doesn't exceed 2 by modulus, by absolute value. And this has zeros exactly when lambda is like that. It's not a proof that it's the right function, but standard 1D theory tells you that. And it also tells you that you're dealing with an entire function with somewhat better estimates than here I have. If you apply it to 1D case, you sacrifice. Since we don't know that much about this function, there are better estimates for this case in 1D than we have in dimension n, but that's what we have. And so the conclusion is that this is not just a some strange singular surface. It is analytic subvariety of codimension 1 in Cn+1. When you say variety, not manifolded, it allows for singularities which you have. And now the proof uses the infinite determinants theory, which you can find in various places. I think buried in your book on trace class ideals, and also there is very nice source, Goldberg and Krein, old book, An Introduction to Theory of Non-Self-Adjoint Operators. It's very nice explanation. So what you do is the following. So let's look at our function, our operator ak of lambda. We know this the formula for HK. It's minus delta plus minus, I think, 2i k dot gradient plus k squared and plus potential and minus this lambda. And this is unbounded operator. It doesn't have anything like determinant, at least at the first glance. But what you can do, you can take an invertible part here. This is an operator on torus. For instance, you take minus delta plus 1 and divide by it. You pull out minus delta plus 1, and so you can include 1 here, changing v a little bit. Then what you have identity plus an operator polynomial with respect to k. Actually, it's a quadratic polynomial, where you will see that those operators are smoothing. Since they were of lower order than delta, and you divide by delta, you get negative order operators. They are smoothing. And smoothing operators on compact manifold, it's a well-known thing that they belong to what is called Schatten-Neyman classes. I will not, I don't want to introduce, it's easy to introduce them. For instance, operators with trace or Hilbert-Schmidt operators are two particular examples. Well, I will say that class SP consists of operators such that if you take their singular values, which are distances to finite dimensional operators, to one-dimensional, two-dimensional, three, etc., approximation numbers, then they belong to little LP. That's one of the definitions. So then, what you see here, you see 1 plus some certain polynomial with coefficients in appropriate Schatten-Neyman classes. And there is a theory, you cannot take the determinant of this operator, but you can take determinant of operator where A is in class SP. But this is so-called regularized determinant, that P. If you take determinant as infinite dimension, it will diverge, but you can correct it, and there is this function determinant. It is known to be analytic with respect to the operator in this class. In particular, if the operator itself depends on parameters analytically, this will be an analytic function of those parameters. And it will exactly give you those kernels. Exactly gives you those kernels. So essentially, you have something like infinite dimension, but much better, since those determinants are well studied, they have estimates, etc. That's how you get this growth. Okay. Here again, my term Flaquet variety, which no one uses, including me, but I needed a name for this. The thing is that Bloch variety is periodic with respect to k. It just repeats itself. By definition, we discussed this last time, and I also mentioned today, that this operator, when you shift k by 2 pi, it's unitary equivalent to itself. And so this variety is periodic with respect to k. And this is deficiency, since we want to, very often we don't want to see this artificial periodicity. Then what you do, you quotient your Bloch variety by this periodicity. Essentially, this means that instead of crystal momentum k, you use what I called Flaquet multiplier z, which is e to the power ik1, e to the power ikn. And that sometimes appears. And so here is this notion. Now the Flaquet multipliers, unlike quasi-momenta spans the whole space Cn. Flaquet multipliers, none of their components can be zero, so they belong to the nth power of the punctured complex plane. And we have seen that in the free case, in the free case, the block variety looks as follows. It is set of shifts of a paraboloid. So you take the paraboloid lambda equals k squared and shift it by gamma star. So if you quotient out those shifts, you essentially get this paraboloid. And now let's notice some features of this. First of all those irreducible components, so you see that this, I didn't introduce the notion irreducible. So what does mean irreducible component? If you have a set of zeros of analytic, if you have an analytic set of codimension 1, we will not deal with anything but that. If you can split it into non-trivial union of two sets, each of which is analytic by itself, it's called reducible. So if you can split S as S1, S2, and each of them separately is the set of all zeros of an analytic function, they're called components. So you can reduce it. You can split it. For instance, if one of the sets is a set of zeros of one function and another is a set of zeros of another function, then if you take the product of those two functions, the set of zeros of the product will be reducible, since it will be just union of two sets of zeros which don't know about each other. So every analytic set can be split into irreducible components. So here we see what they are. Each irreducible component is just a paraboloid. Paraboloid, clearly you cannot split further into union of two sets of zeros of analytic functions. They will have to be the same. So this is what we notice. And if we quotient the gamma star, the quotient will be irreducible. You will get essentially one single paraboloid. Moreover, this component is algebraic. So what we notice that those irreducible components of block variety are algebraic, and the Flaquet variety, if you quotient out this periodicity, is irreducible variety. By the way, we have seen already example of irreducible. In 1D, there is this theorem by Kohn that in 1D dispersion relation is always irreducible. In other words, you can understand irreducibility also in the following way, that if you know a piece of your set, you know everything by analytic continuation. If you have two components that are foreign to each other, you cannot recover from this piece the component S2. They are not related. So if you remember that I mentioned Kohn's theorem in 1D that says that, and it's not hard theorem to prove, but it's important observation, that if you know a little piece, in other words, you know the one of the lambdas for a small neighborhood of quasi-momenta, you know everything everywhere. All lambdas for all quasi-momenta. By analytic continuation, they are connected. So this is, we see that in the free case, this block variety is still, if you quotient periodicity, is still irreducible. We'll discuss why irreducibility is important. If you turn on the potential, normally you will never have algebraic components. They will be analytic, but normally not algebraic. One can construct examples of periodic potentials where you do have algebraic block variety, but those are non-self-adjoint. I don't believe that I know how to do the self-adjoint. in self-adjoint way. That's exactly what I said. Essentially, what you can do to get algebraic component, if you take minus delta and add lower order terms such that they have periodic coefficients with the following property: all Fourier coefficients, non-zero Fourier coefficients are located inside of a cone, which actually forces them to be non-real function. Then one can prove that when you add those lower order terms, you don't perturb this block variety. It also shows that there is no uniqueness in inverse problem if you forget to require self-adjointers. So there are non-self-adjoint operators, periodic operators, which have exactly the same block variety as free Laplacian. But it's non-self-adjoint example. If you, again, quotient out the periodicity, if you look at discrete operators, if you approximate your operator like you have seen already, discrete versions, operators on graphs, etc., then you always get algebraic surfaces. Since essentially in this situation, you are dealing, instead of infinite dimensional operators, you're dealing with finite dimensional matrices. You can take determinant, and determinant of polynomial matrix is a polynomial. So that's what happened. Now about irreducibility. The conjecture is that whenever you have periodic potential, then real valued periodic potential, then the block variety is irreducible. Again, modulo this periodicity. It is very much believed, but the only thing that has been proven that it's true in dimension 2. And the proof is really non-trivial. It's algebraic geometry type consideration, which you have to do in the case when your sets are not algebraic but analytic. So it's pretty involved thing. But it's known in dimension 2. That's the only thing that is known.
And there is no way it could be extended the proof to higher dimension.
What?
There is no way the proof could be extended again.
No one has succeeded in this. No one.
My memory is the proof is close to 1,000 pages. Is that
No. It's several pages. No, it's not their work on algebraic Fermi surfaces, which is a book. Right. No, it's a paper, maybe 20 pages or something.
Okay.
No, it's not that big.
Okay, I'm misremembering which one.
No, it's not that. Another more or less esoteric but still funny question is, what if you don't quotient out your periodicity? You see, in the free case, what you have one single paraboloid, and its shifts, block variety is always periodic, but it consists of unrelated copies of the same paraboloid. They are different components. I have conjecture, which may be a theorem. I will explain why maybe. That if in your block variety, can it happen that your block variety has irreducible component, and other components, the shifted components, are different? In other words, this component is not invariant with respect to any shift. You see, paraboloid is not invariant with respect to any shifts. I think that I have proven, but I will have to check it. I've proven it twice differently. Still not sure that that's correct proof. The claim is that when you turn on the potential, all those formerly unrelated copies, they started gluing together. The claim is that if you have a non-algebraic component and you shift it, there are some shifts that will keep it invariant. So in other words, you turn on the potential and those guys that were completely independent copies of paraboloids, they start gluing together. At least some of them. At least some of them. And I remember preparing those lectures, I remember that I proved this a long time ago. I searched through all my papers and notes and book that I wrote, and I didn't find the proof. I remember vaguely what I used some criterion of algebraicity. So I sat down and I think I found a different proof since I couldn't recall the old one. But still, there is some checking is required. It's not that it's useful. I don't know how useful it is, but it's interesting observations that those independent things, they start connecting. It somehow confirms, works in the direction of confirming the conjectures that Bloch variety is irreducible. Okay, there is a simpler version than complete irreducibility. There is a question which is much simpler and still very important. Instead of saying that, instead of trying to prove that there are no independent components at all, we will try to prove that there are no flat components. In other words, the question is, okay, maybe your Bloch variety is reducible. It might consist of several unrelated components, so this is your Bloch variety. But let us ask one simpler question. Is it true that it never has flat components? If it has a constant, graph a constant function, clearly it's independent component. It has nothing to do with others, so it is reducibility, but it's very limited class of reducibility, so we want to, you will see later why we need it. You will see that many people worked on this, and there is good reason from spectral theory, but let us so far just ask this question. Can we just prove, instead of proving that there is at all one component at all, which would exclude horizontal components, let's try to exclude just presence of horizontal components. And in other words, can we have lambda in C such that this equation has a non-zero solution for all complex quasi-momenta? Here I notice that I use analyticity already, since if you have a small piece of flat component, if it's the set of zeros of an analytic of entire function, it should continue everywhere, just by analytic continuation. And therefore, if you do have a flat component, lambda equals constant in your dispersion relation, which would mean, if you look at the graph, which would mean that you have one band that collapses in the point, single point. And actually we will see that it would mean presence of pure point spectrum. And the idea is that why complexity, here is the place where complexity is very important. We don't care in dispersion relation about complex quasi-momenta, but here the idea is that maybe if we go for k very far in the complex domain, maybe we will be able to show that there is no solution, and then there is no flat component. I don't know how to prove this without going to complex domain. Staying on real k, no one has succeeded proving this.
But by a flat compound, so you mean for all k in Cn, or you mean
yes,
on a hyperplane?
All k in Cn. Hyperplane is in Cn plus 1. lambda is constant, but k is arbitrary. So k, any in Cn. First of all, this thing can happen. This thing can happen, but not for second order operators. For fourth order operators, I've heard claims sometime before that it's true for any elliptic periodic operator. It's not. One knows examples of fourth order operators, periodic, elliptic, wonderful operators which do have flat components in dispersion relation, and fourth order operators therefore can have reducible Bloch varieties, and it's all related to the fact like absence of unique continuation properties for fourth order operators or double characteristic things, etc.
You want to put example for second order?
Yes, I will, but it's with bad coefficients. It only proves that it is something that I will be discussing, that it's something closely related to uniqueness of continuation. That's what he showed. But if you have nice coefficients, this cannot happen. Conjecture is that for any, you cannot have flat components for any elliptic second order operators with decent coefficients. Let's say C infinity coefficients. It's not proven yet. However, you see, there's a whole bunch of good people who worked on this, and it's proven not in the full generality, but I've later on will tell you some exceptions. It's not proven completely, I think, unless Bernie and Sasha will correct me. It's not proven completely in this formulation, but for very good big classes of periodic operators, it is proven that there are no flat components. And later on we will see why people spend their time on working on this. So it will need, it's not just to check irreducibility, but for spectral theory.
Thomas is the real hero.
What?
Thomas is the real hero because he
Yes.
had the idea.
Yes.
He had the idea of going from real K to complex.
Yes, and actually all proofs existing do the same.
Right. They all follow.
I have a different approach, which I think is the only correct one, and which has never worked yet. It doesn't make it incorrect. No, it works in a couple of trivial cases when there are simpler rules. But it's interesting. I will discuss later. Not only for fourth order operators, but also if you look at some, let's say, discrete or graph operators, you can have second order operators with flat components. But this is a fact different, somewhat, not completely different, but somewhat different from the fourth order. It's also due to absence of uniqueness of continuation on graphs. David has mentioned also this, but it's mostly due to the topology of the graph, which can be non-trivial. Okay, so this is about irreducibility. Why did I discuss this? I will not tell you right now. We'll see this when I go to spectral issues. But probably since there's a change of question, it's time to have a break. What, 10 minutes?
It's up to you.
Okay, 10 minutes.
Any questions? Well, I have one question actually. Are there any examples known in the graphs, quantum graphs, discrete graphs, whatever, when there are flat components and they are not due to the lack of unique continuation?
Not due to what?
Not due to the lack of unique continuation. So essentially, eigenfunctions are different. You actually change.
No, there is a theorem. It was my theorem, but then it was proven. The analogous theorem was proven in much bigger generality by Lenz and Veselek. I proved that if you, we will see later that as you well know, presence of this flat component is equivalent to existence of L2 eigenfunction. There is a theorem. If you have L2 eigenfunction on a graph, it's always combination of eigenfunctions with compact support.
On periodic graph.
Yes. But Veselic and Lenz had this in much bigger generality, I think, in situations that are closer to what David discusses. And it's much more complicated theorem. But even for periodic graphs, to prove the theorem, I had to use several complex variables in coherence shifts. I don't know, it's stupid, but I don't know another proof that on periodic graph, if you have L2 eigenfunction of periodic operator, then the whole eigenspace is generated actually by compactly supported one. So it's exactly answers your questions. It's only due to absence of unique continuity.
This theorem holds for both discrete graphs and quantum graphs.
Yes.
Right?
So it's actually weaker than unique continuity. I mean, it's compact support, which is a
Yes.
stronger statement.
Yes,
than unique
it's unique continuation fails as badly as possible.
Right. It's a really bad version.
Yeah.
Right, okay, unless there are further
So
questions.
then it's now what, 5 minutes or something?
7.
7. Okay.